chapter 11, we're going to talk about periodic motion. Sometimes we talk about oscillating motion, simple harmonic motion. All of these types mean the motion repeats with a definite period. We are not doing section 11.1 over elasticity, so you can just start with section 11.2. We call something periodic if that motion repeats over and over in a definite period of time. One of the most common types of periodic motion is called simple harmonic motion. Simple harmonic motion is almost always abbreviated SHM. So if we need to save a little time, SHM means simple harmonic motion. In simple harmonic motion, the restoring force is directly proportional to the displacement. The restoring force is directly proportional to the displacement. Mathematically, that looks like this. F equal Kx. Or if we want to get direction involved, we often will put a negative here, because we'll see with a spring that the restoring force is always opposite to the displacement. If you pull a spring to the right, the restoring force is going to be to the left. If you pull the spring to the left, the restoring force is going to be to the right. This is called Hooke's law. And it applies to ideal springs. You will often see Hooke's law without the negative. The negative is really about direction, which you can kind of common sense the directional aspect, but the size of the force. If we talk about a spring, the amount of force that I pull, if I pull to the right, the displacement's to the right. Sometimes they're in the same direction. The spring, however, will be pulling back in the opposite direction. We can kind of think about this. I'm going to draw a picture. Let me make a little more room on my rather small board. Let the edge of my board here be the wall. And we'll assume that we have some block that's resting on a table. Here's the block. In fact, I'm going to draw several pictures of this same block on this same table. I'm going to let this line right here be the equilibrium line. This is the line x equals 0. So here's a spring. If I'm sitting here at equilibrium, the force is 0. That's the natural place the spring wants to be. However, if I pull this block over, so now I have a displacement of some quantity x. I've stretched this spring. It now feels a force to the left, right? You'll notice that, I'll put an A, we'll call that X. You'll notice that X is positive, but the force is in the negative. It's in the opposite direction, okay? I think that makes perfectly good sense. All of the energy in the system is potential. So when I pull this out there and stretch it, the spring is going to gain elastic potential energy. Okay, we've already talked about elastic potential energy when we talked about conservation of energy. We know that it has elastic potential energy of 1/2 kx squared. If I release it, it's going to immediately go back the other direction. When it reaches this equilibrium point, it won't stop. It's going to travel right through the equilibrium point. Because now, at equilibrium, the potential energy is equal to 0, but it has its maximum kinetic energy. All of the potential energy we gave it when we stretched it has been converted into kinetic energy by the time it reaches that equilibrium. Because of that, it's going to overshoot equilibrium, and it will go until all that kinetic energy, and I guess I better draw my springs. Now it's bunched up. Until it reaches the same distance to the right. At negative x, the force is positive, it's back to the right. Again, the energy is at potential energy. And the kinetic energy is 0. Now, you'll notice if I were to draw a line, kind of from the center of mass, this looks like a wave. It would keep right on oscillating back and forth if I had a taller board and I could draw more. I don't have a taller board, but we get the idea. Let's think about a little bit more about this simple harmonic motion. Now, I've drawn a horizontal situation, but we get the same results if we suspend something from the ceiling. If I hang a weight, oops, I need it to be a spring though. And I find its equilibrium point, where it's not moving. I know that at equilibrium, basically it means that the upward force of the spring and the downward force of gravity must be equal, right? Now, I'm not saying the spring won't be unstretched, because the spring, in fact, will be stretched, but there's an equilibrium position. If you pull this down, you stretch that out, it will experience a situation where the upward force is greater than the downward force, and it will accelerate back up. But when it reaches here, all of this potential energy from pulling it down is going to be kinetic energy, so it won't stop. It will keep right on going, compressing that spring until all of this all of this kinetic is back into potential. Again, it will keep that pattern and repeat it over and over. So you get these periodic motion. Looks much like a wave. Okay, we know that we said that this is F equals negative Kx. If you have an ideal spring, the restoring force of the spring is equal to K times X. It's in the opposite direction of X. K is that spring constant. But we know if this is the only force, if we have a situation like this and we say there's absolutely no gravity, or if it's a hanging spring and we say there's absolutely no air resistance, no non-conservative forces, no energy loss, then this has to equal the mass times the acceleration. And we see that our acceleration is equal to negative kx over m. That makes sense. The stiffer the spring, the larger that spring constant, the more acceleration we would expect. But at the same time, the heavier this mass that we're trying to accelerate, the less acceleration we would expect. So that gives us a relationship for a spring mass system between acceleration and the spring constant and the mass. All right, there's a lot of vocabulary that we are going to need to use for waves and for periodic motion. A little bit of this vocabulary we've already used when we talked about rotational motion. If something's moving in a circle, that is a certain type of periodic motion. It has a definite period of time it takes to make a complete revolution. It has a definite frequency, which would be the number of revolutions it makes every second. So let's go from there. Our first word here is amplitude. In the picture we just draw, it was how far we displace the mass. It's equal to the maximum displacement. But notice I put absolute value bars. From equilibrium. So if you pulled the mass 2 meters to the left, and then it vibrated 2 meters to the left of equilibrium and 2 meters to the right of equilibrium, back and forth, the amplitude would be 2 meters. The symbol for amplitude is an A. Now, and I should have squeezed that in somewhere. We often sometimes talk about the range of motion. That would equal 2A. It's double the amplitude. Amplitude is a linear type of measurement, so both of these, any of these, the unit would be meters. How far to the left, how far to the right of equilibrium, or how far above, how far below. A cycle is one complete trip. You can think of it as being the shortest path before it starts to repeat itself. If we want to start from, say, the origin or the equilibrium, you would have to go out to A, back to the origin, back to negative A, back to the origin. That would be one complete cycle. You don't have to start at the origin. You can start at a point of maximum displacement. You could start at A, go to the origin, go to negative A, go back to the origin, and then back to where you began. But you can see, once you reach this point, you're going to repeat yourself. You normally have to go through that equilibrium point twice. The period is one you should already know. The symbol for the period is a capital T. And of course that is the time for one complete cycle. When we were talking about rotational motion, the period would have been the time for one complete revolution. After that, the rotational motion repeats. Our unit, of course, for period or for any time is always going to be the seconds. We might measure the period of something in days or months or years, but the SI unit will be the second. The frequency which is a lowercase f, is equal to the number of cycles per unit time. Of course, the SI unit would be S. So actually the unit here is seconds to the negative first power. It's per seconds. The number of cycles is something we count. We can say that it was 15 cycles per second, but we don't really usually say that. We usually say it's hertz. 1 per second is 1 hertz, which is abbreviated Hz. Now, if we think for a minute, if frequency is the number of cycles per unit of time, and period is the amount of time per cycle, those are actually reciprocals of one another. The frequency is 1 over the period, or you can say that the period is 1 over the frequency. That's a nice relationship. If we know one, we know the other. So when you read the problem, just pay close attention. What did they give us? If they tell you that something completes 1,500 cycles in 1 minute, then the frequency is 1,600 divided by 60 seconds, or 1,500 rather. Changing my numbers on me. 1,500 divided by 60 comes out to be 25 hertz. If I wanted to know the period would be 1 over 25 hertz. You probably have a reciprocal button on your calculator. Thought I had a reciprocal button. Maybe I don't. But I just don't know where to look for it. That came out to be 0.04. Let's assume we have 2 significant digits, seconds. So, really simple relationship between frequency and period. There is another quantity that is useful mathematically. And that quantity is called the angular frequency. And the symbol for the angular frequency is that omega. It's 2 pi f. The units for angular are radians per second. But again, if you stop and think about it, radians is not a real unit. You can also measure it in hertz. So if you take your frequency and you multiply it by 2 pi, we get this new quantity that we call the angular frequency. The value really is it simplifies a lot of the equations in trigonometry when we start talking about waves. And so there's value in that number. One more example here. It says an ultrasound transducer has a frequency of 6.7 megahertz. I don't know if you know what an ultrasound transducer is, but it's a little transducer that they put on your abdomen when they're doing an ultrasound. Maybe they want to look and see if you've got a kidney stone. Maybe somebody's expecting a baby. They want to look and make sure that all the baby's measurements are right. But it has a frequency of 6.7 megahertz. You might have to get your table out when you see things like that and look that up, but that's 6.7 times 10 to the 6th hertz. Mega is a million. 10 to the 6th is a million. It says find the period and the angular frequency. Well, the period is simply 1 over that number. When you put it in a calculator, be sure to use some parentheses if you need to. It came out to be 1.5 times 10 to the negative 7 seconds. Omega is just 2 pi times the frequency. And it came out to be 4.2 times 10 to the 7 hertz. All right, in this next section, we're going to look at what happens to the energy in simple harmonic motion. Simple harmonic motion is just sort of a repeating conservation of energy problem. The total energy stays the same throughout, but it continuously changes from potential to kinetic to potential to kinetic, and of course at all the points in between, it's a combination. So if we have conservation of energy, it means the total mechanical energy, which we call E, is a constant, and it is equal to the sum of the kinetic plus the potential. I wrote potential plus kinetic at the beginning of the problem, and that sum stays constant throughout. I used initial and final, but we could have just as easily used 1 and 2. It doesn't have to be at any particular point. That will be constant. Now, if we start a situation where we like our spring mass, let's look at our spring mass. Here's equilibrium. And we pull this mass over here, some distance A. So that's going to be X, right? We're doing, now it's all stretched out. We gave it a potential energy equal to 1/2 Ka squared. Remember the formula is 1/2 Kx squared. So if we pull it A, we're going to assume that that's the total energy of our system. That's how much energy we're putting in, okay? So we have a situation now where at any time, the total energy is 1/2 Ka squared, and that is equal to the sum of the potential and the sum of the kinetic. If we happen to be at x equals 0, all of that energy will be kinetic. If we happen to be at the end point, where the object has momentarily stopped moving so that the velocity is equal to 0, all of that energy will be potential. But at all the points in between, this plus this have to add up to equal that. If we want to solve that, we can get an expression for the velocity at any point along the path. And we're going to solve this. First thing you notice is we can multiply everything and all the halves go away. Multiply by 2. And I get that mv squared is simply equal to Ka squared minus Kx squared. If I divide by m, I get K over m, and I'm going to kind of factor that K out. A squared minus x squared, or that the speed at any particular time is given by this expression. You'll notice when we're at our maximum amplitude, whatever that was, this will be 0, and of course our velocity will be 0. If x is equal to 0, then the velocity will be at its maximum value, which is the square root of k over m times a squared. I can put a plus or minus here if I'm thinking velocity, and that just indicates that it has the same velocity, but it passes through every point moving both directions. If we think about it, when it passes through this point, it'll go through it one way and then it'll come back through it another way. Let's look at an example. I don't know if we'll need this formula. I usually don't even use it, but I'm going to write, I think I'm going to want it. I don't even think I want to keep it, but we could. It says a mass on a spring is undergoing simple harmonic motion. The maximum displacement is A. The total energy is E. So we know basically what they're telling us is the total energy is 1/2 Ka squared. Because A is the maximum displacement when it's going through simple harmonic motion, that's going to be the total energy in the system. What is the system's kinetic energy when x equals 1/2 A? So it's asking me to find the kinetic energy when x equals 1/2 A. Okay, let's do that. We really can just use the fact that the total energy is equal to the sum of the potential plus the kinetic, 1/2 Ka squared equals, the potential is 1/2 Kx squared, which is going to be plus K. We're solving for K. No, that's not 1/4, that's 1/8. Why? I have to square that. Let's not go, let's go slower. That's 1/4 A squared. So 1/2 Ka squared equals 1/8 Ka squared plus the kinetic energy. Well, what is 1/2 minus 1/8? 1/2 minus 1/8, that's 3/8 Ka squared is equal to the kinetic energy. There's nothing wrong with that answer, but it's possible that we need to get that answer in terms of E. How many E's is that? Well, I think the easiest way to show you this. We'll do it like a unit conversion. That's essentially a unit conversion. I know that the kinetic energy is, that's supposed to be a capital K, is 3/8 Ka squared. And I know that E is equal to 1/2 Ka squared. You'll notice the K squareds are going to cancel. 3/8 divided by 1/2 is 3/4. We get that K is equal to 3/4 E. So, even though you might think at the halfway point, half the energy would be potential and half of the energy would be kinetic, that's what happens if you're dropping something where it starts off with mgh and it all turns into kinetic on the way down. At the halfway point, it has exactly half of the potential energy it used to have. But it turns out, remember, this is not linear. At the halfway point, it actually only has 1/4 of the potential energy left. And so 3/4 of the energy is now kinetic. Okay, it's not that linear relationship that we had. It might surprise you. We can use that information to make kind of a graph. It's like an energy graph. This would be no energy. And this is going to be E. E is equal to 1/2 KA squared. Okay? When you stretch, this is the equilibrium point. And here is A, and here is negative A. Now, when you are at A or negative A, all of the energy is potential energy. When you're at either extreme, all of the energy. So if I made a green graph for potential energy, it's got a maximum potential energy here, maximum potential at A, it has 0 potential, but at the halfway point, only 1/4, so so it'd be about here and here. Those of you that mastered your Algebra 2 would probably remember that's a parabola. But that makes sense because the energy is 1/2 kx squared. So we would expect the potential energy to be a parabola, 1/2 kx squared. So there's my potential. I'm going to use red for my kinetic. I have no kinetic energy when you release it. I have a maximum at equilibrium. I have none here. The total energy is constant. At the halfway point, my total energy is 3/4 E. So I get a parabola again, only this one is a downward. So you can see as it moves back and forth, we get a continuous exchange from kinetic to potential energy. All right, let's look at another example. I'm not sure. This is our last page. I thought there was a 5th page. Oh, there's a 5th page. Okay, it's all part of the same 3 problems while I was looking. Okay, so let's just consider, this particular example says that we have simple harmonic motion on an air track. Air tracks virtually eliminate friction. It's not terribly important whether it's a glider on an air track or a mass on a frictionless table. We're going to have simple harmonic motion. It tells us, let's draw the picture. So here is kind of what an air track looks like. They're usually kind of triangular. There's some kind of stopper or something here. And it's got a glider sitting on it. I hate that we're not actually in the lab, so you don't get to see this. And it's connected with a spring. It says a force of 60 newtons stretches the spring 0.030 meters, or 3 centimeters. So if I take and I pull on this, I can pull this over and apply a force. When F is equal to 60 newtons, I'm going to move it a distance of 3 centimeters or 0.030 meters. And the very first question, it says this, well, 60 Newton force will stretch it 3 centimeters. What's the force constant? Well, F equals Kx. Notice this time I'm not using the negative because I'm pulling it. I'm applying the force in the direction of the displacement. K is going to be positive. It's really what you just need to know, no matter what. So 60 newtons, 0.03 meters, and I get 200 newtons per meter. That's not right because I left out a decimal. I misread my decimal. 6 newtons. No wonder. I thought we only had 6 newtons, not 60 newtons. 6 newtons. All right, gonna have to start drawing those decimal points darker. So my spring constant is really important. I'm gonna write that little piece of the puzzle down up here. And I have 2 significant figures in case I need to remind myself that I used. Okay, that's without the glider. That's just checking out what the spring constant is with the spring. That's all we were really doing there. And then it says a 0.50 kilogram mass is attached and pulled 0.040 meters from equilibrium and released. So this is our mass. It tells me that my mass is 0.50 kilograms, and then I'm going to stretch it 0.040 meters. I'm going to pull it 4 centimeters. They want me to find a lot of information. What's the maximum and minimum velocity? What's the maximum and minimum acceleration? What's the velocity and acceleration at the halfway point? What's the kinetic energy and the potential energy at the halfway point? It's too much to write it all down. I won't have room to work the problem. So we'll just start with, let's see if we can find the maximum and minimum velocity. I know that the total energy in the system is 1/2 kA squared. If I want to begin with that, I can. And we can start from the very beginning. So I think we'll do that. We could use the formula we found a minute ago, but let's just work it from the beginning. They tell me, so I'm going to have a situation there with conservation of energy that says 1/2 kA squared equals 1/2 kx squared plus 1/2 mv squared. I'm interested in the velocity, so let's solve this again for the velocity. The halves don't go away. I'm going to have kA squared minus kx squared equal mv squared. If I factor out the k's, I can get that v squared, mv squared is ka squared minus x squared. So v is the square root k over m a squared minus x squared. We're going to misuse you just did that. I know, but I think it's really helpful. I can get that formula every time. I don't have to memorize it because I understand this. So our minimum and maximum velocities are the plus or minus. So I'm going to get plus or minus 200 over 0.5 a squared. A is 0.04 squared. The maximum velocity occurs at x equals 0, when we're at that equilibrium point. So it's all I really need is to plug in my numbers. And I get that the maximum is 0.8 0 meters per second, and the minimum is negative 0.80 meters per second. They did say velocity. If they said what's the maximum speed, the maximum speed is 0.80 meters per second. The minimum speed is, of course, 0. The minimum speed is going to happen when x is equal to a. When x is equal to a, that's where you're changing signs on your speed. You're going from positive velocity to negative velocity. Right there, you've got 0 velocity or 0 speed. But 0 is not really the minimum velocity if we're thinking negative velocity is the minimum. All right, let's think about the maximum and minimum acceleration. We know that F is equal to negative kx, which is mass times acceleration. When we're talking about the force, the restoring force, it's negative kx. So our acceleration is negative k over mx. So our maximum is going to happen. Well, let's think about it. The maximum means this is positive, which means x is negative. So the maximum is going to be at x equals negative a, which in this case is negative 0.040 meters. So a max is negative 200 times negative 0.04 divided by the mass. And it comes out to be 16 meters per second squared. Our minimum, of course, is exactly the same, only negative. I'm going to double check it. I want to make sure I didn't do anything wrong. 200 times 0.04 divided by 0.5, exactly 16 meters per second squared. The third part wants to know the velocity and the acceleration at the halfway point, halfway between equilibrium. So we want to find the velocity and the acceleration at 0.020 meters. I'm not going to rework this time. So they want to know the velocity at x equals 0.020 meters. Again, I'm not going to worry about the sign because it's possible that it can be both. Well, I guess I will worry about it. I'll put that it's both. We have 0.04 squared minus 0.02 squared. All of that's put in a calculator, and we see that the velocity at that point is plus or minus 0.69 meters per second. It passes through every point going both directions. The exception would be the two end points because it doesn't pass through those. But when it heads towards an end point, if it's going to the right and it passes through this point once, it will also pass right back through. The speed at that point will be the same, but the sign will be different. Okay. The acceleration at that point is pretty easy. We said acceleration came out to be negative kx over m. And again, it will be both directions, No, that's not true. It will always be opposite the direction of the displacement. So if we're going to have a positive, if the displacement is to the right, the acceleration will be negative. So at that particular point, the acceleration comes out to be negative 8 meters per second squared. That makes really good sense. We know the maximum acceleration was 16 meters per second squared. The minimum was negative 16. At the halfway point, the force is exactly half. Well, if we have exactly half the force, then we should have exactly half of the acceleration. The last thing that they asked us to find was the kinetic energy and the potential energy at the halfway point. Let's just erase all of this. We haven't actually calculated the total energy in the system. The total energy in the system, 1/2 Ka squared, is, let's see, that's going to be 100 times 0.04 squared. The total energy in the system that I got was 0.16 joules. At the halfway point, that's the total, to the potential at x equals 0.02, that would be 1/2 200 0.02 squared. So if I do it 100 times 0.02 squared, that is 0.04 joules. That's the potential energy at that point. The kinetic energy, I'm going to get two ways. The easiest way, this is the total energy, is to subtract. The kinetic energy should just be 0.16 minus 0.104. Which is going to be 0.12 joules for the kinetic. The other approach for the kinetic is we already found the speed at that point. We could say it's 1/2 mv squared the v was 0.69 meters per second. It had better come out to be 0.12. We've got 1/2 times m times 0.69 squared, and it comes out to be 0.119, but to two significant digits. There it is. This one's a little better in the sense that we didn't rely on a previous answer. This was pretty much given earlier. This one, if we had messed up on the speed at the halfway point, we wouldn't have gotten the right answer. And this had a little bit of rounding here. We possibly should have carried an extra digit, but still came out to two significant digits to the right spot. All right, I'm going to stop here. There'll be a second video and we'll finish up this chapter. read this part.
In New Jersey, the governor says he's trying to avoid a wider shutdown of businesses and schools. But he says many of his state's outbreaks can be traced to private gatherings and homes, where the rules are tougher to enforce.
It's serious. There's no question about it. And it's really